Ready? Good morning, everybody. Hey, Jason wanted to bring this up. Everybody we've got the class 3 and 4, probably got the letters to start turning in your CEUs by, I think, July, you got them turned in by. Jason found out for the people that got 1 and 2s that also have 3s and 4s, some people were getting notices you had to turn your hours in. You don't have to turn them in if you hold the class 1 or 2, and so you don't lose your hours. So he got that clarified for us. Also, for one of my guys that turned their hours in, your new hours, they don't start counting again until July. So for the few months, you can still go to this stuff. You just can't use those CEUs. They told him. I'm like, okay. So they don't actually start over until July. Kent Cox from Illinois Rural Water, for people that belong. I think probably most of you do. They got a new wastewater training assistance program with Get Your CEUs. There's some stuff on their website right now that you can watch and get the credit for. I don't think you can get the certificates. Or do you know, can you, Kent?
Which one?
For Illinois Rural Water.
For the Laguna University?
For what?
Laguna University?
No, it's just CEUs on different things that they've come up with so we get credit hours. They got water and wastewater ones and combination, I believe, too, on your website, just to help us all get our hours. Because I've had a lot of conversations with Ken over the years where there was plenty of stuff for water, but nothing for wastewater, or very little. So they're really trying to get more stuff for the wastewater side, and Ken's kind of taking charge of that.
There's 10 hours of wastewater CEUs on Laguna University. The link is on our website.
Okay.
Go to the Laguna University on our wastewater training page.
I think I took that. I think I watched some of those because I wanted to get some more hours, so I think I watched a lot of those.
I talked to one of the guys last week, the week before.
Okay.
When you go, you got to click on Laguna University, then you'll go to another link that says Laguna University, and that'll take you to their site where you sign in. You got to have password. There's 13 recorded webinars. Only 10 of those are good for Illinois. So you want to go back a page. The first time you click the Laguna University on our web page, you'll come up with a highlighted, oval, aqua colored. There's 10 of them listed. Those 10 are the ones that are good for Illinois hours.
Okay.
So you want to make sure you watch one of those. After you watch them, you'll get a certificate, but it does not have the EPA number on it because they're good for several states. That's where you click on the highlighted one at that page, and it'll print you off the CEU form already. You just got to put your name and number on it. It's got the Illinois EPA number and everything's on it. The state
Okay.
There's 10 hours there.
Okay, I didn't do that one. I did something else then. So, okay. That's good to know.
Yep.
I mean, easy way to get some hours, and
Yeah, they're all recorded free.
so.
You won't get your link once you put your password in. It won't come up right away like some. Might be a few hours before you get your email to confirm. It might be the next morning.
Okay.
But, the only thing I've heard is don't stop it and try to click back on it in the middle of it to watch it, because it won't let you. Once you turn it on, you got to watch the whole thing.
The 45 minutes, hour sessions.
They're all an hour.
Okay. All right. Thank you. If there's no other questions, I'll introduce Mickey Menard he's our big pump guy. We're actually getting one of our new lift stations, or replacing the lift station with Gorman Rupp pump station. Pretty impressed with the tour I took at their place. There's no waiting on supplies and parts like some of our lift stations. We might be waiting 6-8 months to get a pump in. Their factory actually has all the parts right on the shelf, and you can usually get them 24 hours. for the most part?
48.
48, yeah. It was pretty impressive when I went there for the first time. I was like, okay. I think you'll probably go through some of that stuff.
Yeah, I'll go a little background of what I am.
But for that one part of the company he represents, the Gorman Rupp pumps are pretty impressive. And everybody knows how many pumps I got over in Germantown, so don't laugh, Jason. So it's kind of a new venture for us to try this style. It's got a little natural gas backup motor that runs the pumps. There's no generator. It only turns on or starts when the calls for the pump to run. No floats, a little air bubbler. I was real hesitant and went to a few sites where these stations were. I'm like, this can't work. Not with all the grease in these things and wipes, but it's pretty impressive. Pretty impressive. So I'll let Mickey take over.
All right, thank you, Rich. I got to figure out how this thing works. So while I'm figuring this out, I'll talk a little bit about who I am and what I am and why I'm here. So again, I'm Mickey Bernard. I work for Hydrokinetics Corporation. I kind of own the place, but I also work there. So there's a difference between being an owner and an employee. And I'm both. So, and part of what I'd like to do today is we're going to play a little game called Stump the Pump Guy, all right? So if I talk about something and you want to jump into that conversation a little bit deeper, I'm not sure if that's going to work. Just let me know. I mean, I don't have a canned presentation. I have a go-by up here, but there's really no direction that I have to go. What I have to do is make sure that I touch on topics you guys find interesting, okay? So as I go through this, if you can't derail me. All right, like I said, I'm with Hydrokinetics. Actually, May 27th of this year, the company will be 25 years old. We do about everything there is to do in water, wastewater, south of here. All right, just about up to this band is where my territory changes. So most of you probably deal with the Northern Illinois representatives for things, but we do represent Gorman Rupp all the way up to Wisconsin. So that's what brings me in this part of the world. And Peoria Sanitary District here, Greater Peoria Sanitary District has used our pumps for a long time, and in the last few years I've been working with them on different projects, and then Rich talked about doing this. So I greatly appreciate the opportunity to talk. Please realize I'm not here to sell a thing today. All right, that's not my intention. You're going to see lots of different pictures of different types of pumps. The goal is to talk about what happens after you buy your pump. You know, we talked about calling it do's and don'ts when you're dealing with pumps. I can call it, buyer beware too, because when you buy a new piece of rotating equipment, and today we're just going to focus on pumps, it's pretty easy because you get a warranty period, right? You're going to get it in, you're going to run it. If it breaks, you call them up and say, hey, this thing broke, come fix it. And hopefully somebody shows up and they do that for you. But if you've had a pump station for 15 years, 8 years, 12 years, and now you have a pump that's out, and maybe you don't like who you bought it from, maybe you don't like the product because it didn't perform the way you wanted it to, or maybe you just want to put a brand new one in because you liked it and it worked well. All of those things factor into decisions that you all have to make on a regular basis, okay? And one of the things I've learned over 37 years of doing this is the vast majority of our pump community, our users, don't really have the time to focus on how do I replace a pump. Because you put the pump in, it's underwater, it's sitting in a building, or it's down in the basement, and it runs until it doesn't, right? Everybody's happy as long as it's chugging along and doing its job, and the minute it quits, now it's an arm-waving emergency. So what do I do? Well, you may not be armed with the right terms or the understanding to ask the right questions when you want to replace a pump. And that's bad. I mean, that's not bad that you don't know it. You're at a disadvantage against people like us, okay? I'm on the other side of that line most of the time, standing there I'm trying to get to where your checkbook is. And if you don't ask me the right questions, how do I know that I'm giving you the right information? Or how do you know if you ask me a question, the information I'm giving you is right? Now, that's a problem. And it doesn't take a lot to understand how all this works, but it's a different world that I live in than you live in. And I can give you can ask me one simple question, and I'll show this a little bit later, and I give you 3 or 4 different answers that are absolutely right. And I can, in good conscience, I can wake up in the morning and look myself in the mirror and say, I gave them what they wanted. Now, what you wanted or what you asked for may not be what you needed. So as we go through this, I'm going to kind of identify different things that I believe you all should know so that you can better make decisions that are in the benefit of your community and your operating performance and your plant and all those things. So as I go through this, like I said, if there's questions, just let me know. Oop, wrong way, I think. All right. As I was talking about, now I do this presentation a lot, but I don't memorize it. So as I kind of go through it, I apologize because I'll read a little bit and then I'm going to start talking. But just like I said, when you're buying a pump, you need to know what you're doing, and you want to be the type of you want to be the piece of equipment that you want to do the job. Okay, so how do we get to that point? Pretty simple. A pump. What does a pump do? Pushes water. We got flow and we have head, right? All right, and then we have horsepower. I need 300 gallons a minute at 25 feet ahead, and it needs to be a 7.5 horsepower motor. Pretty simple, right? Call up 1-800 I like pumps. Ask somebody to get that for you. Well, one of the things that would be interesting to know now that we're replacing it, because the first question I'll ask, why did the other one break? Because I don't want to put my foot in that same bear trap that somebody else just put their foot in, because I may not be any better than they were, because I don't know why it failed. So a little forensic work on your side would be great to know when you call someone up and say, hey, I need a new pump. Because there are reasons why they fail. I mean, pumps are one of the simplest pieces of equipment you probably have in your plant. So, but when they fail, they can just quit. I mean, we're going out to look at a pump station after this with the folks at Peoria here, and I've been told it's somewhere between 1958 and 1978 that was put in. So I'm not exactly sure when, but that's a long time for a pump to be in. So if it's done its duty, all right? So that chances are to replace that pump is not going to be terribly difficult. I mean, it's just, let's find a pump that works in there. Dimensions. How many people have submersible pumps here? Submersible pumps are a lot like boats, you know. The happiest day you have is when you buy it, and the second happiest day is when you get rid of it. So when you replace a submersible pump, there's certain things you should know dimensionally. You know that elbow that sits down at the bottom, it's got guide rails on it, you put the pump down and clunk, it goes into place, and everybody's happy then because you can't see it, but you turn it on, the water goes down, so it must be doing right, okay? Well, some things that you should know is the center line of that horizontal elbow has a dimension to the floor. And that pump that's there and comes down, if my elbow is the pump volute, and this is the top of the pump, and it clips into place or it slides down, I have a center line of where that discharge of that new pump is, right? But I also have a dimension underneath that from the center line to the bottom of my volute. And that's going to be different between pump manufacturer and nobody builds the same way. It's not like an AWWA butterfly valve that's the same valve no matter what you do. And that difference between the bottom of the volute and the floor can either be success or disaster. And not many people know that. And I will venture to say not many pump people know that. So you need to have a certain amount of room. So if you put a pump that has now a larger volute and it goes closer to the floor, what's going to happen? You run the risk of cavitation. You can't get water to that pump because there's not as much room below the pump as there was before. Simple thing like that is the difference between winning and losing, especially with submersibles. You can't hear them. You can't see them. So it could take 2 or 3 years before it fails, and you call the pump guy up, he says, oh, I don't know what, it sounds like a problem. Want to buy another one? So what you need to do is understand that can influence it. Just something simple like that, okay? Those are important things. All right. The other thing that we all need to know is the system. Anybody know what a system curve is? Anybody care what a system curve is? I do. I'll jump up and down and tell you I really care about system curves. Because in the world I live in, is solely based on applying a pump to a system curve. And a system curve, we'll go through what they are in a little bit here. But that's how I know how the pump is going to react, all right? I'm going to take all your piping and all your elevation and all your elbows, and I'm going to put them into a magic little program that I wrote. And I'm going to push a button and it's going to say go, and it's going to tell me that at 200 gallons a minute I have 28 feet ahead. Well, now I got a roadmap. Because I can't just pick a pump, and we'll go through that. I have to know where that pump needs to be on the pump curve. And then the other thing that we need to always keep track of, and what you need to verbalize, what's your voltage? You know, dual voltage motors are great. You know, you get actually you can do 3 voltages, but 230, 460, if it's a standard dry pit pump, you can do that. But today in some parts of the pump business and submersibles, you're going to get a dedicated voltage. So if you buy a 480 volt and you got 230, it kind of hurts, okay? So just keep track. These are all things you need. Keep track of this. At the simplest point, when you walk away, just get a notebook in your pump station. Just write that kind of stuff down, all right? Know what these things are, so that when that situation arises that you need a new piece of equipment, you're kind of ahead of the curve a little bit. You're not scrambling for that information. All right. Now, just as an overview, you know, I live in the smooth water and I live in the lumpy water world. Okay. Now today I'm talking about lumpy water, but we do the smooth water pumps do the same as dirty water pumps. So you have a raw water pump lift stations, you have high service pumps, filter backwash pumps, booster pumps, sludge pumps. The only reason I bring this up is each one of these are a dedicated type of application. You're not going to put one into the other and mix them around. It just doesn't work that way. Typical applications for wastewater: lift station pump, headwork pumps, terminal lift station, grit pumps, process pumps, which are RAS, WAS, dewatering equipment, feed pumps, non-potable water booster pumps, and effluent pumps. Every one of those in there potentially, not even potentially, are all centrifugal pumps, but each one has a different type impeller. Okay? If all I have is a size 9 shoe to sell you, I don't care what size your foot is, I only have a size 9 shoe. So you're going to fit into a size 9 shoe. If I have to cut the toe off so your foot will stick out the end, that's what I'm going to give you. But each one of your process application locations in your plant, and some in your collection system, are specific to that application, and the type of impeller that you get can also lead to a better story at the end. And it doesn't seem that way, but I can tell you, and we'll talk a little bit about impellers here, there's a difference between a vortex impeller, semi-enclosed impeller, shrouded impellers, hardened impellers, axial flow type pumps, which is a little bit different, but we'll pretend like they're the same for this presentation. But each one of these has a place in our world. And if your favored vendor only has one style of impeller, I would suggest that maybe you widen your search a little bit to other vendors that may have different styles of impellers that may offer better service for specific applications, okay? That's just the facts of life. All right, and again, just different size pumps. I live in the little pump world, and I live in the big pump world. So we just sold a booster pump, 2 pumps that were 3.5 horsepower. Last year I sold 4 pumps that each pump pumped 210,000 gallons a minute. So I kind of understand the differences between big and small and what makes the difference. But the ones you own are special to you, all right? So make sure you understand how we get to where we're going to. This is, again, just another typical example of a dry pit pump. This happens to be a dry pit submersible pump. And I don't represent KSB, all right? I'm not here to advocate for them. Matter of fact, they're a competitor of mine. But those are good pictures for you all to see different types of pumps so that you understand there's different things. And if you don't have a dry pit submersible or you don't have the need, then that's not a big deal. But if you have a lift station that's a canned lift station, you have to go down in the stinking ground to get into it and look at it. One of my least favorite things in the world to do are climb into holes in the ground, and especially when they're full of sewage and electricity. But I do that a lot, and at the end of the day, sometimes a pump like that for replacement is the right answer, because then if it floods, you still can pump, and you don't have to go down the hole to fix everything and get it back up and running again. You eventually will, but it will still pump. And again, big pumps, you know, my adage is, it's easy to fix a big problem with a little pump. I don't mean this badly, it's only money, but the money to fix a big problem with a little pump is everybody, it's manageable for everybody. A little problem with a big pump becomes unmanageable very quickly. It becomes something that you just don't want to live through. So if you start buying 50, 70, 100, 200, 300, 500 horsepower pumps, spend time on those pumps, all right? Understand what that means from a maintenance standpoint. Understand what that means from a operations standpoint, whether it be starting and stopping them. All of the things that go into buying that pump are very important as they get bigger. And just, again, booster pumps, that's a split case pump, that's a smooth water pump. That went into a little town next to St. Louis. That's at the Quincy Water Plant. Now, this is kind of a hybrid. You don't usually see a split case pump put on raw water. That's pumping Mississippi water on a suction lift to the Quincy Water Plant. So, and that's a replacement pump that put in probably 15 years ago, and they're tearing that pump station down now, and they're putting real raw water pumps in, because a split case is not the most ideal pump to be pumping sandy, gritty water. Nothing wrong with the way it pumps, it's just not really necessarily the right pump for the job. This is what Rich talked about with his pumps. These are self-priming pumps, which are what we're putting into his community. I put this up there just to show everybody that it can get a little confusing when you start selling pumps and you get into situations. With this particular pump, the pump station, there's 3 pumps. And with that pump, you can turn on one pump and it'll run in parallel, and you turn the second, or one pump, it'll run in simplex. Any one of the 3 pumps you turn on, it will series connect to the next pump and give you twice as much head. So Mount Pulaski, just down by Springfield, they had a pump station, a can pump station. We put the parallel series pumping in because they would have had to dig up a mile of the streets in their city to put a new force main in. They said, we really don't have the money to do that. So by seriesing a pump, all right? So if I put a pump in parallel, you turn one pump on in a normal pump station, 100 gallons a minute. Turn on the second pump, how much do you think you're gonna get? Just roughly, guess. Twice as much? If I get 200 gallons a minute? You get something less. Typically you get 5 to 8% more flow. And then we'll talk about that on the pump curve in a little bit. What does that mean to me as a pump owner? And what does that mean to me from a maintenance standpoint? How do I get out from underneath the problem? If you take those same 2 pumps and you turn the first pump on in simplex, you get 100 gallons a minute. And if I can push the water through the second pump and make that boost it and go up, now I can probably get, instead of 107 gallons a minute with 2 pumps running, I might get 150, 175 gallons a minute because you cut the head in half. So now my velocity losses at the higher flows are shared between 2 pumps. Okay? I can spend hours talking about this. Okay? So I'm just saying, understand there's ways to fix things with standard centrifugal pumps. Booster pumps, this is interesting. I bring this up. Anybody do potable water here? We all wastewater folks? Okay, some potable water. Even in your non-pot systems. These are pump control valves. Kind of confusing, but it's basically put in there to reduce the velocity potential of starting and stopping a pump. Simple words, it takes water hammer away. But again, it's just one more doodad thing that's out there that you have to look at and understand how it fits into my pumps. What is it that I own? Kind of a deal. All right. Most critical item selection and the application of pumps to determine the operating system curve. There's that pesky system curve again that I talked about. The second most critical item is matching the new pump to the existing system. That's that piping thing I talked about. All right, so now we need to know what the system curve is. I need to know how much water is going through that pipe and how long that pipe is, because that pipe is not going to change. It's not going to change. The only thing that's going to change are my elevations of the water. That's the beauty of what we do. So you'll need to know the system curve. And the third most critical item is knowing why the pump failed. Circle back. What's the first question I ask everybody? Why are you calling me? I'm always amazed because I don't know very many people in this business, all right? I know the people who I deal with all the time. And so when there's a new voice at the end of the phone, again, most of the time I'll ask, why'd you call me? What's the deal? I don't know you. What would certainly make you think that I can help you? And it's usually because there's a pump failure and somebody says, well, I need your help. And so then now all my questions start. Say, why are we talking together and how can we make it better? All right. As I said earlier, pumps are a very simple mechanical piece of equipment. They spin, hopefully in the right direction. Anybody wire a pump up wrong and have it run backwards? Sounds like hell, doesn't it? A pump running backwards will pump half the flow and half the head. So let's just say I've been just a pump station this week that pumped from here to that wall away to a manhole. If I wired that pump backwards, it would pump. Wouldn't be a very happy pump, but it would pump. So just realize that the issue you get with that is going to be just vibration that's crazy, and it's going to be a really unhappy pump, but you can have that. They have a defined diameter. All right, diameter of the impeller. It's going to be part of the pump curve we're going to read when we learn what a pump curve is. All right, diameter impeller is important. A couple different ways to change the flow through a pump. I can take that impeller and I can trim the tips off. If there's 2 tips, I do this, or there's 4, and I have 4 of them, and I can change that from a 12 3/4 inch diameter to a 12 1/2 inch diameter, and I'm going to get a little bit less flow. And it has to do with how the water goes through the volute and the cut water and the things that you really don't care about. But that's how I can change it. So I can make it, but it becomes less efficient. Or I can change the speed. Put a VFD on that bad boy, slow it down, let it march up and down the system curve, and I can reduce the flow. Both of which have issues, both of which have been done forever. One of them is a technology issue with VFDs. If it breaks, they don't just grow VFDs on trees, so it's kind of hard to get that fixed. If you're constant speed, trim the impeller, you lose some efficiencies. So you're spending a little bit more money to pump all the time. So those are trade-offs that you have to get into. All right, they have a specific speed, which I won't get into, but that has to do with the pump curve. They produce a given flow at a given head related to a defined and complete system curve. Holy cow, the system curve keeps showing up. What's the system curve stuff that I'm supposed to know about? All right, system curves. Define the operating parameters for all centrifugal pumps. And I should probably put another never in there, but never, ever select a pump for an application and then determine the system curve. That's what I'm saying to you all. Do not call up 1-800 my favorite pump guy and say, I need 200 gallons a minute at 58 feet ahead. Don't do that. Understand why your pump needs 38 feet of head. The pump doesn't know. It just spins. Given diameter, right? Specific speed. You turn it on and it spins. Doesn't care if there's even water in it. It's going to spin. Why do you need 38 feet of head? What makes 38 feet of head happen? If you understand how your pumps are applied, you'll be able to troubleshoot your own pumps and many times fix the problem before you have to call anybody. And it takes a little bit of work, but you can do it, all right? So, always evaluate the potential for the system curve to change due to system variables. Changes in static head. Who knows what static head is? I do. All right, pump station. We usually pump down, what, 2.5 feet? So I got, on levels at 4 and I turn it off at 2. Runs that way every day. The difference between that on level and off level and where we're pumping to is the static head. That's extremely important to know that, okay? So I got a pump station down in the hollow by the creek, because then I can overflow into the creek, but we would never do that. But it's down at the bottom of the hill, and I'm pumping up 25 feet. Before that pump ever turns on, before that pump even does anything, the check valve is closed, clunk, that pump already sees 25 feet of head. All right, a little over 10 psi. So it's sitting there waiting, right there. So I have to overcome that static head before that pump will impart enough energy to push the water up the hill. And that static head changes by the difference of how much the pump pumps. So maybe you have a EQ basin at your plant, and it's a 10 feet tall tank, and I've got a Headworks pump station that's 100 yards away, down 20 feet in the ground. Well, now I got 20 feet in the ground, and when that tank is full, I have 10 more feet of head against that pump than when that EQ tank is empty. Well, that makes a difference. And when you select a pump, you got to know what that means. You need to know what that means, because, again, that's the difference between success and failure. And there's reasons we'll talk about as we go through this. All right? So you have multiple pumps in a common force main. I just talked about that, pumps in parallel. Be very careful. We'll talk a little bit about placing pumps in parallel and what you do, because many times you damage the pump. My contention is in lift stations, small lift stations, you're better off letting the wet well level rise 2.5 feet than turning that second pump on, because it forces the other pump, the second pump, or both pumps, to the left of the pump curve out of what we call the AOR, the allowable operating range, which can damage seals and bearings and things like that. So it's good to understand that part of the hydraulics. And then the demand on the system, and that's really more in the potable water. I got a pump over here and I got a tower over here, and how am I filling that? And we do a lot of SCADA work, so we need to understand where does that water really go and how does it go there and how fast does it get there and how do we react to it and make sure the pumps can follow suit. All right, here we go. That is a well-placed pump on a system curve. That blue line is the difference in static head, all right? And for this, it looks like it's 3 or 4 feet, maybe. So when I start and stop, that pump is going to change flow just by a little bit. Let me find this, if I can find the pointer on this without turning this thing off. All right, perfect. For those of you at home won't be able to see this, but right here is what I'm talking about. That's the difference from when you start and stop the pump. It's pretty simple, pretty small variable, but right here, I'm pumping 3,050 gallons a minute. Well, I get out here, and I'm probably pumping 3,100, 3,200 gallons a minute, so I pick up a couple of feet of additional flow because my system curve is lower. Think about it. I got that tank we talked about. It's 10 feet high, my EQ tank at the wastewater plant, and I got my pump station down here. Well, if I have that tank low because we don't have a big storm event coming, and that tank is empty, when I turn that pump on, that pump does not see as much pressure to pump against. So it's going to want to walk out. Oh, hold on. It's going to want to walk out to the right of the pump curve. Because I have less pressure, I'll be able to get more flow. wonderful. This is we don't have to do anything. The whole world works perfectly because of the difference in elevation, right? Well, we're going to see what happens if that bottom curve ends up out here. Well, you ordered a pump for right here. I don't know what your system curve is. I don't care what your system curve is. You called me up and said 3,050 gallons a minute, 192 feet ahead. Bring it on. And I'll give that to you. I don't know. I'm fat, dumb, and happy at that point, okay? All right. Impellers. Just kind of keep, this all kind of winds up together. Kind of keep in mind there's a purpose to this. Lots of different impellers out there. I talked a little bit earlier about that. Sometimes it doesn't make a difference. A difference is only a difference if it makes a difference. And in 80% of the pump applications, a standard centrifugal impeller will do just fine. Everything will be great. But those specialty applications of maybe high head, long stringy material, gritty material, it makes a difference if you get the right impeller in there. So you can have an enclosed impeller. So you take your submersible pump apart. And I'll pick on a brand because I know lots of people use it. Flight. How many people have the old Flight CP3102s? You know, they're the old style. You take the volute off and you got this impeller. There's a shaft sticking down into the impeller, and there's a shroud on the top and there's a shroud on the bottom, and the impellers are kind of in the middle in a sandwich. One piece of an impeller. I'll show a picture of one. That's a standard centrifugal enclosed impeller. It can't do anything except whatever that duty point is at this given speed. You have a semi-closed impeller. The Gorman Rupp pumps are what we call semi-enclosed. I have a shaft with an impeller, and then I have a cover plate that has a wear plate on it. When I push it up against the volute, up against the impeller, it encloses it then, okay? So now I have a way to trap that energy. I got some way to take that water and that energy that I'm imparting through the motor and get it to go up and out, okay? And then there's open impellers, which are more akin to the Vortex and open, or somewhat the same, where you just let the volute geometry make the flow rate go. The water never goes through the impeller itself. It just spins it really fast and then goes across the cutwater and zips up the line. You have multi-vane for high efficiency. The more vanes you can put into a pump, the more efficient it gets. The bigger the impeller it becomes, the more efficient it gets. Because now we have a lot more room to push water through an impeller when we make them, okay? Little bitty pump, chances are you're going to run at 3,600 RPM because you're just trying to get the water out of it. Let's get it going. You can get a great big pump, and it'll react and offer better service because your volute velocities and your impeller velocities are much lower. All right, and then you have single vaned impellers, which are typically a shrouded or enclosed impeller. And here we have them: enclosed, Vortex, grinder, and then the E impeller, which is the single vaned impeller. All right, this is the inlet nozzle. This is the bottom of the sandwich of bread. That's the top of the sandwich, and your impellers are right in the middle. That's the tip I talked about that we would trim. Vortex impellers. My number one voted most favorite impeller in the world is a Vortex impeller for small lift stations. 15 horsepower and below, because the fluid never passes through the impeller, so they don't choke off very easily. And if there's grit, it doesn't wear the impeller out because it doesn't go through the impeller. Now, it is the most inefficient pump known to man. It is just terrible, but it's a lift station. It's going to run 8 times a day. Do we really need 72% efficient? Is 32% efficient okay? You know, what's more efficient in a pump? A pump that's really efficient that you have to go out and take clogs out of, or a pump that's really inefficient that you don't have to take clogs out of? Vortex impellers just work well. They do a nice job, and they're relatively simple to troubleshoot, and you're never gonna get anything caught in the impeller. It will not happen. So, and again, these are just examples of what we're trying to get to is we're trying to buy a new pump. When a pump is misapplied, bad things happen. Discharge cavitation. Your system curve is too far to the left. Okay, and I'll show an example of this. The closer you get to shutoff head, everybody know what shutoff head is? Anybody ever run their pumps to shutoff head just for fun? Okay, that's when you close the valve and the pump is pumping to a dead head. Shutoff head is 0 flow. And that will be the highest head that that particular pump will produce at that particular speed. So if you want to just, for the pumps we do with GR, one of the tests we do when we start it up is we close the valve and turn it on and take a gauge reading. And that gauge reading should be the combination of the speed and the impeller diameter to the left-hand axis where it goes to 70 feet. And if it does that, which it should if it's a brand new pump, everything's good. But over time, you want to test that. Man, has my pump worn any? How do I know if this thing's working right? What do I do with it? After a year, I go out there and I close the valve, take my gauge reading, and if it's within 2 or 3%, it's 69 instead of 70, I don't have too much wear in there because that pump is producing the right amount of pressure at the right speed. 5 years go by, go out there, all of a sudden now instead of 70 feet of shutoff head, I'm at 60. All right, well now I know I have wear. What do I need to do? And there's different procedures and things you can do to troubleshoot a pump to figure that out, but that's an easy way to do that. All right, so you get discharge cavitations on the left side of the pump curve. That's where they've got a pipe that's too small, too long, too high of static head, whatever those are. You can't fix that one. There's nothing you can do if your system curve is too steep and it's to the left side of the pump curve. Whatever's making that happen is unfixable. That pump is just misapplied. Suction cavitation, true cavitation. Too much suction pressure, all right? My self-priming pumps have to pull water up. We only have 33.4 feet of atmospheric pressure in this part of the world pushing water down. Does everybody understand how a pump works? Everybody know what atmospheric pressure is? Keeps us from floating around the room, all right? Pushes us down, pushes water down. Well, when you turn a pump on and it starts to spin, the water comes right up through here, and that's what we call the eye of the impeller. Right in the center of the impeller is the eye of the impeller. If that's surrounded by water and you turn it on, you will create a low pressure at that point, lower than atmospheric pressure. So atmospheric pressure is pushing down on that fluid in your lift station, all right? And as that atmospheric pressure pushes down and you create a low pressure here, atmospheric pressure wants to stick its finger down and get to that. I want to get to that low pressure. Where is that low pressure? I want to get to it. And in doing that, it pushes that great big mat of water down, and then these impeller tips right here come across a cutwater and they evacuate the water out because atmospheric pressure keeps pushing more water to it, so I got to get the water out of there because we're trying to get atmospheric pressure to this thing, and that's how a pump works. Atmospheric pressure. You run out of atmospheric pressure, the pump will cavitate. You can boil water two ways. Rise it to 212 degrees and it'll boil. Or you can reduce the partial pressure of the fluid, which are a lot of big words that mean basically if you take and go to the lab, in the lab, wherever it is over here, and take a vacuum and reduce the pressure inside a beaker, you can boil water at room temperature. Just because you're reducing the pressure on it. Water can pop out then. Atmospheric pressure is pushing that water and keeping it in its state, in its liquid state. So when we run out of atmospheric pressure, we're going to cavitate. When we cavitate, you begin to tear the pump apart. Again, why did your pump fail? Well, I took it apart and the impeller looked like hell. It was all chewed up and chipped up and looked like somebody took an ice pick to it. I'm like, okay, show me a picture. I love pictures. I love stories. Tell me what this thing is. And if there's a bunch of deterioration at the eye of the impeller, that's where we ran out of atmospheric pressure for your application, okay? And when we run out of atmospheric pressure, we boil the water inside your pump, and it sounds like air. Somebody will go, oh man, you got a bunch of rocks, you got air in that pump. Not so much. It could be just vapor pressure, vapor bubbles. So the water boils, these little bubbles form, just like when you're watching the pot on the stove. And as we move toward here, compared to here, this is a high pressure area, this is a low pressure area, and you're going to get a bunch of deterioration right inside here and right inside here, those impellers, because as those vapor bubbles come out, they implode. All right? They bang, they come together at a pressure of 80 to 120,000 psi. So if that's next to a piece of cast iron, it's going to chip it away. So if you ever taken one out and it looks like Swiss cheese, you might have an NPSH issue. And this is more typically found in dry pit pumps. Long suction line. Somebody closed the suction valve. Something clogged the suction of the pump. Whatever is, then you're making that pump. It's spinning, creating, it can go to 33 feet. It's going to pull vacuum until it can't pull vacuum anymore, and it is going to destroy itself. My question is then, why'd your pump fail? Tell me your story. I like stories. All right, you can get shaft fatigue. Shaft fatigue is because of discharge cavitation. I got a real high pressure onto the left side of the pump curve every time it goes past the cut water. If I'm running 1800 RPM, I got a 2-vaned impeller, 3600 times a minute. I cut across the cut water, and I have a high pressure and a low pressure, and it's like taking a hanger. And eventually, if I keep doing this in front of you guys, what's going to happen to the hanger? It's going to break. And that's what you get when you run at high discharge head, to the left of the pump curve. You'll get seal damage at that point, you'll get bearing damage. And the thing that's most irritating is downtime. We can fix the mechanical stuff. You can buy parts, you can put it back in, and we can wait for the whole circus to start again and have that. But during that time, that's what you have, is downtime. So how do we fix that? What are we after here? This is what we're kind of getting to. We're talking about system curves, we're talking about impellers, we're talking about pump curves, we're talking about speeds, we're talking about all these things that you all really need to know. Because somebody's going to ask you, how come we have so much overtime? Or why do we have to rent pumps? Or, what are we doing with X? And we'll say, well, we're waiting on parts, and we'll figure it out. Well, why did we do that? Well, we bought a new pump and it only lasted a year. Okay? Let's fix that. All right? You can have backups, low pressure, flooding, none of which are any type of pleasing event. All right. Flow and head are only part of the story. The media being pumped. Hello. The media being pumped. We pump in sludge, we pump in water, we pump in sewage, we pump in grit. What are we pumping? Each one of those things brings an opportunity for success or failure. Installation location. That goes back to, is it a suction lift? What does my piping look like? How deep is the wet well that I'm pumping from, or to where I'm going to be pumping to? Suction lift, flooded suction, mechanically sealed. Some of the larger pumps have packing in wastewater. That's kind of a nasty opportunity, but it exists because water goes everywhere all the time. But these are all things. Okay. Is it time to quit? Do I need to leave? So, okay. These are things you understand what you're buying. Understand what it is. Write this down. Make a list of each of your pumps. So when Jim walks in and says, pump station 3 failed or pump number SP7 failed, you go to your sheet and say, okay, well that's my RAS pump. I know what the voltage is, I know what the impeller diameter is, I know what all this stuff is, I got it right here, and now I understand what that is rather than just an opportunity to call 1-800 my favorite pump guy. Seems like a simple application. Ask 5 distributors for this pump, and you will get 5 or more different selections. 1500 or 56, remember that. 1500 or 56. They don't care about efficiency. You didn't ask me about efficiency when you called. You said you wanted a pump, right? I'll give you a pump. They don't care about horsepower. Oh, your motor starters are only good up to 60 horsepower. Oh, well, I'm giving you a 75 horsepower pump. Huh, I'll be darned, look at that. They don't care about sump dimensions, crazy little thing called HI standards. How does the sump look? That can affect the efficiency of the pump. There's a lot of things that go into this. And then they don't care about existing piping, valves, or fittings. Just don't care. I wasn't asked to care, so I'm not going to care until I need to. The number one thing, understand, they're there to take your money. They are there to take your money. I'm there to take your money, okay? That's my job. I believe in what I do thoroughly and wholeheartedly, that it's a fair bargain. You know, when you go buy a head of lettuce, and you go home and you make a salad, I paid $3.20 or whatever it is, and tomorrow it'll be $4.20, but you can make a salad, you eat it and say, man, this is the best salad I ever had in my life. I'll go buy some more lettuce, okay? If you pay for the right thing, the dollar value that you pay is the bargain that you get back that it's going to work. You don't ask the right questions, you're not going to get a fair bargain. I don't care what it is. You don't know what if you don't know where you're going, how do you know when you get there? Okay? Understand these things. These are important. The next is hoping that not to ever see the installation. And now this is from the pump guy's standpoint, or pump girl, or pump person, however you want to define us. But, you know, I want to sell it to you, ship it to you, and never see you. Just send the check, bring it on. And finally, making it through warranty without issues. 366 days, checking them off. Free. You need a part? Send me a purchase order. That's what happens when you don't know what you're buying. Bottom line. And I'm in this. I mean, I'm the bad guy. All right. I'm the one that you're angry with. Okay. So you need to understand why the bad guy's standing up here, because I believe more than 80% of my job is education. I just deal with pumps. I mean, I got into this business. My background's water treatment process. I'm a process guy. I just learned pumps because I was a project manager in Oklahoma, and the guy I worked for said, you're going to go figure out how that pump works, and I don't know how pumps work. He says, well, by the time you come back, you'll know how a pump works. I said, okay. So I learned how pumps work. But I had to go through all this. I had to figure it out. Not very many people taught me this stuff. I picked up the pump handbook and read it and learned it and understood it, because I did not want to be in that maddening crowd. Did not want to be there because people get angry. I'm too old for that. I'm just too old to have people yell at me. So I don't need that. All right. Always provide complete information. This goes back to, where's my little sheet of paper? Got to write this stuff down. We're going to see what it is. Accurate flow and head. Gauges. If you don't have gauges, buy gauges. If you have gauges and they don't work, throw them away. Worst thing you can do is put a bad gauge on a good pump and get bad information, because then you don't know how the pump's running. Differential pressure. That's all a pump does. I got this pressure coming in, I got that pressure going out, and I put that onto the pump curve. And now I have a point on my system curve, because the system curve is the iteration. It's the repeating. I take your pipe, which is 1,000 feet long. I got my 25-foot of static head, and then I know that I only pump 2 feet down, so I'm at 25, 24, 23, 2 feet down. So then I have another line that comes up, and I go through, and I plot how much pressure it's going to take to push water through that pipe. So I take a 10-foot stick of 4-inch PVC pipe, and I put it on my shoulder, put a golf ball in it, and I let the golf ball go. What's going to happen to that golf ball? Golf ball, let it go, putt, bang, through the hole. It'll run down the pipe pretty easy, right? Nothing to stop it. That golf ball is just zipping down the pipe. Take that same golf ball, my media, my water, the golf ball, has not changed in size, diameter, weight, texture. Nothing has changed in my golf ball. I take a 10-foot piece of hose, garden hose, and I put that on my shoulder and put the discharge down there and I put my golf ball there, what's going to happen? Nothing. Now, laws of physics will tell me I can get that golf ball to go through that hose. It's just going to take a lot of pressure. Water is the same way. The more water you jam through a pipe, the more pressure it makes. Okay? You got these walls of a pipe, and the pipe create resistance, and that resistance turns into pressure. So my system curve is really just at 0 gallons a minute. I have my static head, my 25 foot. Nothing on, pump is waiting to start, got that 25 foot ahead sitting up to the top of the hill because the pipe is full of water. Turn the pump on and I look at it at 10 gallons a minute, 20 gallons a minute, 50 gallons a minute, 800 gallons a minute, 1,000, 2,000, 3,000, and I plot those numbers and I figure out how much resistance is in your system, so I can apply the pump. I look at what's there. Now, I'm not suggesting you all go out and start doing system curves. But I am suggesting that when you get a pump station put in, you get that data from your design engineer and keep it. Get that data and put it with that little piece of paper that I told you about. Because then, when 1-800-MY-FAVORITE-PUMP guy sends you a pump curve, you can place that system curve dot by dot on that curve like I showed on that blue curve, and you can decide, is that a good place for that pump to run? Maybe, maybe not. But now you're in control. You know the questions to ask. You can't be buffaloed. You can't be bullied into this is what you should do because all the rest of your pumps are this pump. And most importantly, you understand how your system works better than the pump person does. With that, you will get success. All right, accurate flow and head. System data, static heads. Have suction and discharge gauges. Back to gauges again. If I have accurate gauges, I can place those and take the differential head and go to my pump curve at the speed the pump is running, put a dot right there. I don't care about amps. Motor shops come out and they diagnose pumps with amps. I'm like, really? That just tells me what the motor's doing. I don't care what the motor's doing. If the motor's on and spinning and it's doing its job, I need to know what that hydraulic end is doing, and that's with gauges. That's what you need. You have to be able to understand what gauges do. All right, job site voltage, maximum allowable horsepower. You don't want to have it overloading. Installation drawing and dimensions. If you walk away with anything today, know that stuff. Know that stuff. And if you have pump stations and you still are working with the same consulting engineer that you had before, tell them you want that stuff. And they'll probably look at you cross-eyed, what do you want that for? That's what you hire us for. And you say, well, I'm just curious. I'm just a curious person. I'd like to have that. All right, always ask the right questions. If you cannot find someone who you're going to buy a pump from who will not give you a certified pump curve, move to the next pump vendor immediately. You want a certified pump curve of any pump you buy that you can put in the file and take out and say, oh, look at that. This is what it's supposed to do. This is the real deal. That's important. Know what the AOR and POR is. Allowable operating range, preferred operating range. What is the non-overloading horsepower? Helps you so you don't have any switchgear problems. What type of impeller is provided? Just interesting to know based on maybe how it failed. What are the materials of construction? Cast iron, stainless steel, brass, bronze, whatever you want to put into that. Where's the closest repair facility? How long does it take to get spare parts? And does your company represent the pump manufacturer? Some people just go out and buy pumps. They don't represent anybody. They'll go to Grainger and buy a pump and then sell it to you. Make sure you're dealing with a certified, authorized sales and repair center. All right, real quick, because we're getting to the end of this deal. This is my AOR, where the red line is. That's the allowable operating range. This little shaded area is the POR, preferred operating range. 1500, remember I said 1500 at 56? Well, that pump will do it. And there's my high static and my low static. So I'm right here, and my high static. That pump is never going to turn on. If that pressure's that high, I'm never going to run. But you only asked me about right here. There's another one. Same deal. 1,500 gallons a minute, 56 feet ahead. Well, I can hit it right there. But when I go and hit the high static, I'm going to be way back here. I may be at 700 gallons a minute because the high static system head curve is making me run right there. Same application point. Nothing's changed. Now this looks pretty good. 1556. I'm out here. I got my duty point. Now understand, because the static head is different, I will lose flow because I can't do anything about the physics of how the pump works. But at least it's still in the AOR. It's on the pump curve. Not too bad. Not a bad option if I had to pick that particular style of pump. And then here's one that's passed, again, 1500. I'm just trying to show you that you're going to get a wide variety of people selling you things, know what you're buying. This looks really good. Not too much difference in head. The steeper the curve, the less variation you'll have on static head changes. Conclusion, buying the wrong pump can be expensive, can create undesirable issues, to say it nicely. Somewhere, sometime, somehow you'll have to deal with replacing a pump. Know what you need, keep accurate records including system data, pump type, required duty conditions, accurate pump curves, and good things will happen. That's a lot of information, I get it. I would start with the basics. Find out what you have in your system and start writing it down. And then when you do have a pump station put in, get the system curve. And understand that just because you ask for it, be careful what you ask for. Because you may exactly get what you asked for, but it may not solve your problem. Any questions? I threw a lot of stuff. I do pump schools that last all day long, so some of this I kind of rifle through, so I apologize if I went quickly. I can spend 2 hours on system curves. I can spend an hour on gauges and troubleshooting. I can talk multiple hours on NPSH characteristics and things like that. I can put almost anybody to sleep. I'm confident of that. But and if you have questions, I'll be happy to answer them. If there's any.
I had a slide back there on I think it was on potable water pumps, and you said it was to reduce water handling.
Yeah.
Why wouldn't you use a VFD on a situation like that?
The simple answer is, one is cost. The other is location to replacement parts. Because if you don't have a vendor close enough to you to buy a new VFD and it quits, you're stuck. And we sell a ton of custom controls. And there's two things that create a great deal of angst after the fact. One are submersible transducers. Because when you go to buy a new submersible transducer, like, my God, how much does that thing cost? It costs $2,000. I'm like, that's what it costs. I don't know what to tell you. Float switches for $40. We could have done float switches. I'm okay with that. And the other are VFDs and soft starts. Because A, nobody knows how to program them. B, when they break, you got to buy a new one. There's no, let me see if I can get the wrench out and fix it. So across the line, bang, motor starter with a pump control valve, because what we're doing is controlling velocity. All right, you think of a pipe. Pipe's going up this hill, going to feed a tower, and you turn your pump on, and I'm doing this for the city of St. Louis right now for some 5,000 horsepower pumps. We're pumping 60 million gallons, so that's 42,000 GPM up a pipe. So if that pump stops here, that water keeps right on going, man. It's on a mission. It's heading into the city of St. Louis, and then where it gets to one of the reservoir, which is a ginormous pool of water that is in essence immovable. That 60 or 42,000 gallons a minute going into a 20 million gallon reservoir, that 60 gallons, 42 gallons a minute doesn't do anything to that water. So it's like hitting a brick wall. Bang. Hits that water. Now, that water that kept going creates a low pressure down here, a change in velocity. So I was at 100 PSI. Well, now back here, I'm at 80 PSI or 75 PSI. So when that water hits that reservoir, it's like, holy cow. I got lower pressure back here. I better hurry up and get back. I gotta get back to where that pressure's low. So that water comes rifling back and then hits the pump station. Bang, another brick wall. So it goes up and down and up and down. That typically, the average in steel or ductile iron pipe is about 4,000 feet per second is the energy wave. And a thing called a critical period. And the critical period is the time it takes to go up and hit that wall and come back. So when you put a pump control valve in, you want to slowly close that valve and slowly open that valve in no less than 10 critical periods, so that you change the velocity of the fluid gently. Because water hammer is the instantaneous change in velocity from 0 to 100 or from 100 to 0. And that's where you see pipes breaking out of the ground. At home, turn your water on, the pipes, bang, bang. You ever have your pipes do that in your house? It's just water hammer. It's just the velocity change. That's all it is. So in something like that, that was a very, very rural area. And a funny story about that was that pump station. And when I went and started it up, pump stations here, towers here, there are 2 houses in between, about 2.5 miles. So I set up the pumps. I'm just doing my job. And I set the timing on the valves to what I thought would be reasonable for a slow startup and slow shutdown for the pump, because the valve starts, the pump starts against a closed valve and it opens real slow. And then when it goes to stop, the stop signal tells the valve to close, it closes, and then when it gets almost closed, it tells the pump to turn off and then finishes closing. So I've taken that velocity gradient and broke it down a great deal. So it was a Friday, got the pump station done. Monday, the mayor calls me. He says, Mickey, we had a little problem. And I don't remember the woman's name. Mrs. Jones was out watering her garden, and she said the water quit coming out of the hose. And so Mrs. Jones decided she didn't understand what was going on, so she took the hose and looked at it, and that's when the pressure wave came back and blew water all over her. So Mrs. Jones was not very happy. But that was a classic example of that, the change in pressure, because I didn't have the valves set up right. So that water had a lower pressure, so it just quit coming out, and then bang, it came back out. So it's critical that you get that right from personal experience. Anything else? Well, thank you. I greatly appreciate the opportunity to come talk to you all. If you do have questions, I would be happy to answer them and help out any way I can. Just please do your community a favor, do yourselves a favor. Do some documentation. Know what you're doing. And it can go for blowers, it can go for pumps, it can go for any rotating piece of equipment. Just be careful. That's all I'm saying. There's good people on my side of the business. I shouldn't knock them all. I mean, there's some very good, conscientious, well-intended people that do a good job and they care about their customers and the outcome. But there's a portion that would just there to take your money. So just be a little bit careful with that. Thank you again. Appreciate it.